Welcome to The Explainer. Today, we're zooming way in to look at the fundamental building blocks of our civilization. We're examining what a lot of people have basically called the absolute wonder material of the 21st century. Yep, I'm talking about graphene. It is, quite simply, the strongest, thinnest, and most conductive material humanity has ever managed to discover. But here is the massive question we really have to answer today. Is this material truly the future of everything, like an absolute S-tier revolutionary that's going to redefine human engineering from the ground up? Or when you strip away all those flashy headlines and the crazy venture capital funding, is it actually just an overhyped, incredibly expensive lab experiment that kind of only works under perfect conditions? Well, we're going to look strictly at the data to find out. Okay, let's dive into this and brutally evaluate these claims. Here is our roadmap. 1. The atomic superpower. 2. A Scotch tape Nobel Prize. 3. Exposing the flaws. 4. 2026 applications. And finally, we lock in that definitive tier ranking. Section 1. The atomic superpower. Going 2D with pure carbon. So to actually grasp the mind-bending theoretical specs of this material, we first have to understand what it actually means to go two-dimensional. By definition, graphene is just a single layer of carbon atoms arranged in a repeating hexagonal lattice. Honestly, it looks a bit like molecular chicken wire. Now, if you imagine the graphite inside your standard pencil, the stuff you write with, graphene is essentially just one single, isolated, one-atom-thick layer of that exact same material. By isolating that singular layer, we create something so unbelievably thin that physicists fundamentally consider it two-dimensional. And let me tell you, dropping into that 2D space unlocks properties that honestly sound completely made up. Now, what's really interesting about this slide is the sheer impossibility of these statistics when you put them side by side. Check this out. It has a tensile strength of roughly 130 gigapascals. What does that mean? It means it is over 100 times stronger than structural steel. To break it, you would literally need to balance an elephant on a pencil and balance that pencil on a single sheet of this stuff. Yet it sits at a thickness of 0.34 nanometers. It is literally a single atom thick. And on top of that insane strength-to-thickness ratio, the electrons inside travel with practically zero resistance, meaning it actually conducts electricity better than copper. Oh, and it possesses some of the highest thermal conductivity ever measured, it's completely impermeable to gases, and it's almost 98% transparent to visible light. So yeah, it's basically invisible armor that conducts electricity perfectly and dissipates heat instantly. Crazy, right? Section 2. A Scotch tape Nobel Prize. Tracing the revolutionary story. To really appreciate graphene, we've got to look at how this futuristic superpower was physically brought out of the realm of pure theory and into our actual world. If we trace this timeline, we can see graphene isn't just some academic fantasy anymore. It has a very clear evolutionary path from the lab bench straight to the factory floor. So it was first successfully isolated back in 2004, and the impact of that isolation was so profound that by 2010, just 6 years later, the discovery won the Nobel Prize in physics. Fast forward through the 2020s, and after years of intense R&D, we started seeing the very first commercial products hit the market, things like enhanced batteries and specialized conductive inks. And now, looking at the landscape today in 2026, we are seeing the rapid, massive scaling of graphene oxide and few-layer graphene production. This scale-up is absolutely critical, guys, because it marks the definitive moment graphene transitions from a boutique scientific curiosity into a viable industrial reality that can actually change global supply chains. But listen, here is my absolute favorite fact about this entire timeline, and I think it perfectly highlights just how bizarre scientific discovery can be. That 2004 isolation by Andrei Geim and Konstantin Novoselov at the University of Manchester, it was achieved using mechanical exfoliation. Now, that is a very fancy, highly academic term for taking a block of graphite, literally pencil lead, and repeatedly sticking standard everyday Scotch tape to it. They just peeled it back over and over again until only a single layer of atoms remained on the adhesive. No billion-dollar particle colliders, no giant lasers, an entire new scientific field of 2D materials, a multi-billion-dollar industry, and a literal Nobel Prize were all unlocked with basic office supplies. I mean, you can't make this up. It's just brilliant. Section 3. Exposing the flaws. Time for the brutal reality check. Okay, it is time to leave the hype cycle behind for a minute, because turning this laboratory miracle into actual scalable products has been an absolute nightmare. The contrast here is incredibly stark. Theoretical graphene is a dream. It's unmatched in strength, perfectly conductive, and exists in these pure, flawless sheets, stretching out to infinity. But look at the manufacturing reality. Graphene suffers from massive dispersion issues. What that means is when you try to mix it into a liquid or a polymer, it desperately wants to restock itself back into normal graphite. So you get these useless clumps instead of a nice, even distribution. On top of that, producing large, defect-free, pure sheets is just wildly expensive. And ironically, a single macro layer of pure graphene is actually really brittle and tears super easily if it doesn't have a rigid substrate underneath to support its structure. So the crucial point is we have to ruthlessly list these industrial hurdles because they are exactly what holds the material back from world domination. High-quality graphene remains remarkably expensive to produce at any meaningful scale. Like we just talked about, when you try to mix it into plastics or liquid resins to make advanced composites, those dispersion issues mean you get isolated clumps instead of an even, strong spread. And scaling up large continuous sheets, which is exactly what we need for things like touchscreens or solar panels, well, doing that without introducing microscopic defects that totally ruin the electrical properties is incredibly difficult. Plus, researchers are actively dealing with genuine health and toxicity concerns regarding the inhalation of microscopic graphene oxide flakes in those manufacturing environments. And finally, you just can't ignore the sheer environmental cost. It takes high energy demands and incredibly harsh chemicals to mass produce this stuff right now. Because of all these persistent headaches, as of today, it actually still frequently loses out to older, much better understood technologies like carbon fiber and carbon nanotubes when it comes down to raw industrial cost effectiveness. Moving on to Section 4, Real-World Applications in 2026, Escaping the Lab. Now, despite those massive flaws we just laid out, graphene is officially escaping the lab by acting as an incredibly powerful additive. Take a look at how it's being deployed in modern engineering today. The biggest impacts are hitting in batteries and supercapacitors. Mixing in just tiny amounts of graphene drastically lowers internal resistance, which gives us incredibly fast charging and significantly higher energy capacities. It's also becoming absolutely crucial in enhanced composites, basically reinforcing polymers to make aerospace components, automotive frames, and even sporting goods exponentially stronger and lighter. We're seeing it completely revolutionize advanced coatings, creating these hyper-durable anti-corrosion and anti-icing paints for shipping and aviation. It's pushing the boundaries of next-gen electronics and flexible wearable sensors, and it's even doing incredible work in environmental filtration, acting as a sort of molecular sponge to absorb industrial pollutants. Make no mistake, without these targeted applications acting as a catalyst, our current progress toward lightweight, hyper-efficient future technologies will be moving much, much slower. And here is a really surprising trend for 2026 that perfectly demonstrates where this material is actually heading. Graphene has moved entirely beyond just small tech and specialized electronics. It is currently undergoing commercial-scale pilot testing in concrete and asphalt. Yes, civil engineers are literally mixing microscopic amounts of graphene straight into our heavy infrastructure. This tiny little addition adds massive durability. It prevents microcracks and drastically increases the total lifespan of roads, bridges, and buildings, all with almost zero added weight to the mix. It's a completely counterintuitive application, but it is proving to be genuinely revolutionary for the global construction industry. Finally, Section 5, the final tier ranking. Zero mercy, no nostalgia points. We judge the materials of our civilization with zero mercy, so let's put graphene through the definitive gauntlet. For historical and tech impact, it easily gets a 9 out of 10 for single-handedly sparking the entire 2D materials field. Mechanical properties? A flawless 10 out of 10. On a structural level, it is simply unmatched by anything else in the universe. But look at workability. It drops to a 7.5 due to those incredibly persistent clumping and handling issues during manufacturing. And this brilliantly illustrates the real issue, because scalability and cost take the absolute biggest hit at a 6.5 out of 10. It is still premium priced and agonizingly hard to scale flawlessly. But versatility and lasting relevance both bounce right back up to a 9.5 out of 10, because its potential to actively upgrade dozens of distinct industries is just completely undeniable at this point. So despite those heavy hits to its scalability and workability, the sheer perfection of its mechanical properties and its massive future versatility really keep it afloat against our harshest critiques. When we average those scores together, the final number for graphene comes out to a highly respectable 8.7 out of 10. Which means our official verdict places graphene solidly in high A tier. Now, its current cost and the really harsh realities of industrial scalability prevent it from taking that absolute top S-tier rank right now. But make no mistake, it truly is the atomic blueprint for the future. It remains one of the most exciting paradigm-shifting materials humanity has ever managed to tame, and it carries absolutely massive upside for the decades to come as manufacturing finally catches up to the science. Now, graphene might be a high-tech wonder of the 21st century, but for our next explainer, we're doing a total 180. We'll be looking at salt. That's right, salt. It's ancient, it's remarkably simple, it preserves our food, and it melts our ice. But is it actually possible that this incredibly basic, everyday mineral might outrank our futuristic, one-atom-thick wonder material on the definitive tier list? Will salt literally season its way to the top? Well, you'll have to join us next time to find out. Until then, keep questioning the world around you.